Our next speaker is my nemesis, Matt. so Matt, you may have seen recently, he just tweeted like an hour ago that everyone comes to him complaining about TensorFlow bugs, and I'm one of those people. And so today, Matt's going to tell us like how amazing TensorFlow and Keras is. But what he actually does at Hugging Face is also maintains the TensorFlow side of the Transformers library. And he's a great speaker and has a lot of great humor. So I'm looking forward to plenty of jokes.
No promises.
All right, so let me get the stream.
Yeah, we'll disappear from the stream and.
Okay, so this, fingers crossed, is working. G'day, this is Lewis.
Hi, so this is going to be a quick talk about new features we've added to the Hugging Face libraries, particularly for TensorFlow and Keras users. So there's one particularly important feature I want to show today, which saves me a huge amount of repetitive boilerplate code, and it also improves the memory usage and performance of my training by a very large factor. So to start, I'm just going to set up a standard sort of training run, and then we'll see how we can use this method to save us a lot of effort and to improve our performance significantly. So we're just going to start. I'm going to start by loading a dataset. So we need the load dataset function from the datasets library. And the dataset I'm going to use is the COLA dataset from the blue benchmark. Oh, sorry, load dataset. Okay, so if we look at this dataset, it's very straightforward. There's only 3 columns: the sentence, so the text, the input for each sample, the label, which is just 0 or 1. So this is just a simple binary classification task. The model is predicting whether a sentence is valid English or not. And then the third column is just the unique index for each sample. So this is pretty much as straightforward as NLP tasks get. But even here, this method is going to be really useful. So what do we do when we have our data? First thing we do in almost all NLP tasks is we tokenize it. So we're going to import our tokenizer. And today feels like a Distilbert kind of day. So we'll use our model as Distilbert. So tokenizer equals auto tokenizer. Okay, so that should give us the Distilbert tokenizer. And now there's a cool trick for applying these things for tokenizing datasets, and that is to use the dataset.map method. And I'll show you here. If we just make a quick tokenization function, and all the tokenization function does is it just tokenizes the sentence key of whatever dataset you pass it, because the sentence key is the key that contains all the input text for each of these samples. Then all we need to do to tokenize all of our datasets is to use the dataset.map method and map that function. Sorry, tokenizer. And here we go. And now we should have our datasets. So a cool thing here is that when you use map, if your function returns a dictionary, all of the keys of that dictionary are going to be added to the dataset as columns. So the tokenizer returns a dictionary with input IDs and with attention mask keys, and both of those are now in the dataset as columns, and that means that all of our data is sort of kept together. We can pick out any single sample and see both its original text and its input IDs and its attention mask and so on. So it's really handy for kind of organizing your data this way. But that's not that feature's been around for a while. There's something new I want to show you, and that is the 2TF dataset method. So why do we need this method? So to see why, let's look at the input IDs. So I'm just going to pick out the training data set. I'm going to pick out the input IDs here. I'll just put that in a variable called tokens. So the input IDs are the tokens that come out of the tokenizer. And if we look at tokens, we see it's just a list of lists. So each sample has been turned into a list of integers like this. And now if we just check the lengths, so I'm just going to say len sample for sample in tokens. So that's going to give us the length of every single sample. We see here the lengths and they vary. So there's quite a range of lengths. They're mostly around the same length because they're all like one sentence. But even one sentence can have a varying number of words, and each of those words can be split into a varying number of tokens. So there's quite a lot of variability in terms of how many tokens there are. In fact, if we look at the max, we'll see that one sentence has ended up as 47 tokens. And if we look at the mean, we'll get that from the statistics library. We could have also just divide sum by length. That would work as well. We see the mean is 11.5. So if the max is 47 tokens, but the mean is 11.5, the longest sample in that data set is almost 4 times, in fact, slightly more than 4 times as long as the average. And that's a problem because if we want to turn this data set into one single tensor or one single array, we're going to need to pad every sample to the same length. And particularly when I want to train with Keras, it's really, really helpful if I can get the data in one single array. That's something I really want to do, because then I can just pass it to Keras and Keras will handle, it will sample from the data, it will shuffle the data, it will make batches for me. I don't have to worry about any of that. But it's pretty difficult to do that here. Because if we have to pad all the samples to the length 47, pretty much 3/4 of our data is going to be padding tokens when we're done. And that means our data set is going to be 4 times bigger than it needs to be, which is going to be a big waste of memory. And it's also going to slow down computation enormously. In the case of the COLA dataset, I mean, these are not huge samples. Even 47 tokens is not that big. Language models can handle inputs from 128 to 512 tokens very easily. And there's more specialized models can go way beyond that. But these, even though we might, we could sort of get away with padding everything to the maximum length for COLA, it's still a big waste. And for other data sets, it's an enormous waste, and a waste that would probably make the task impossible if you had to do it. So in general, padding every sample to the maximum length is not something we want to be doing regularly. But if we don't do that, then we can't put all the data in a single array, and that means we can't pass it easily to model.fit. What I personally ended up doing was writing generator functions a lot of the time, and that generator would have to handle shuffling and sampling and batching all the data for me. And it just meant I was writing the same code over and over and over for every task I wanted to do. I would have to write this huge generator, and it was a big source of small bugs would often be in the generator, and it would be just a big annoyance to debug them. So what I want is some way that I can pass the data to TensorFlow without having to write all that boilerplate code, but without padding every sample to the maximum length in the data set. I only want to pad each batch the minimum amount required to make that one single batch a tensor. So the solution we came up with is the 2TF Dataset Method. And I'll show you how that works here. But the first thing we're going to need before we use it is a collation function. So a data collator is a function that puts together samples into a batch. So you can write your own, but we've got a range that covers pretty much all of the common collation methods you would need to use. So probably the single most common is the data collator with padding, and that's exactly what we need here. We need the data collator with padding data collator, and then we created we initialize it like so. We say data collator with padding. It needs the tokenizer, and the reason it needs the tokenizer is that different models have different padding styles, and so it needs your model's tokenizer, so it knows how to pad data in the way that your model expects. And the second thing it needs to know that you want TensorFlow tensors back. Because these data collators and our tokenizers are all framework agnostic, which means they're designed to work with both PyTorch and TensorFlow and even with JAX. So you need to be very careful that you tell it the type of tensor you want back, so you don't accidentally get PyTorch tensors or some other horrible, undesirable thing in your lovely TensorFlow code. So if we run that, we now have our data collator. And now we can convert the data set like so. We just say, we'll start with just the training data set. So we'll just say tokenized datasets train, and then we call the toTF dataset method. And what it needs to know is it needs to know the columns, which is going to be which columns of the data set are we going to be passing to our model. So we can see here that those are almost always the columns that were added by the tokenizer. So we can just put that in there. So those are the columns we want to go as our input. We can also add label columns. So these are the columns that are going to be passed as the label in each batch, and that is labels. It's also, you'll see it's marked as label, but our data collators rename the column label to labels because almost all models expect the input to actually be called labels. Just a minor quirk that will be, the data collator will take care of it for you, so don't worry about that too much. But just be aware of that as an interesting quirk of most transformer models. And then the other things we need are, we just need to tell it that we want the data to be shuffled, and we want a batch size of 16. So these are arguments that you would normally pass to fit. But when you're generating your data outside of fit, for example, with a data generator, these are the things you need to take care of yourself. The toTF dataset method needs to know whether you're shuffling and what batch size to output for you. But I've tried as much as possible to keep these methods close to the same Keras arguments. So you just move these arguments from fit to toTF dataset, and it should work in the same way. And then the final argument we need is the collate function. So the argument is collate function, collate fn, and we just pass it the data collator we initialized already. And of course, I just realized we actually need to save that as a variable and not just run it on its own. So if we run that, this is just TensorFlow initialization, don't worry about it. And if we look at our data set, we see we get this nice data set out. So it's each batch, this is showing you sort of the shape of each batch that's going to come out of the data set. So you can see that each batch is an input dictionary. The keys are attention mask and input IDs. It also gives you the shapes and the types for those. And then the second element of the tuple is a label here. And it's just a one-dimensional vector with shape 16. So that's exactly what we want. And the great thing is this data set is just ready to go. So now all we need to do is compile and fit our model. We'll just get our optimizer. So it's from TensorFlow to Keras.optimizers Atom. And the reason we are doing it this way and not just calling Atom by string is, of course, that we need significantly lower learning rates for Atom than the default. Atom by default has a learning rate of 1e minus 3, but with transformers, something like 5e minus 5 is usually much more appropriate. So that's almost 20 times lower. In fact, exactly 20 times lower. And the second thing we'll need is to import our loss. And our loss, of course, is sparse categorical cross entropy because we're doing a classification task. And again, this is something you can call by string. When you're calling model.compile, you can just pass these as strings. But it's not advisable to do that with the sparse categorical cross entropy loss. And the reason for that is that all Hugging Face models output logits, not probabilities. So logits are the values before you apply a softmax to them. So a softmax turns raw logits into your output probabilities. And so you should be aware that the sparse categorical cross entropy loss in Keras expects probabilities by default. And if you want to pass it logits, you need to make sure to tell it that that's indeed what you're passing it. So that means you need to import the loss and then set that argument correctly. But now we have both of those. We can import our model, and we can, so this is going to be a 4 sequence classification model because this is a sequence classification task. And our model is going to be just going to initialize it with a standard from pre-trained method, and we're using we're going to make sure that, of course, we use the same model here that we tokenized our data with up here. So at this point, everything's been initialized. It's just telling us that some layers were newly initialized because it added a classifier layer, and that we're going to need to train this model before it can actually classify anything. And that's, of course, exactly what we expect. So now we can simply compile the model. We have our loss. We have our optimizer. So that all works. And now the beauty is we can just pass this straight, our trained data set that we made with the 2TF dataset method, we can pass it straight to model.fit. Give it a second to compile and put everything together. And there's our model. So this is a very quick script. There's a very quick script. There's very little, I might have said a very quick crypt there by accident. I don't think we're burying anything. But the key thing to take away is just that there's very little code here, but this setup will give you minimal memory usage and maximum performance because the data is only being padded just in time. So each batch is coming out and it's being padded at the very last moment and only to the minimum size needed for that batch. And that means that we're not wasting any padding tokens. Whereas if we padded the whole data set, we would have a huge amount of padding tokens and everything would just be much slower and we'd be bloating our memory usage massively. And without the 2TF dataset method, we would need to write a generator and collator ourselves to do all of this. And it would be a huge amount of boilerplate code that would be a source of bugs and just a big waste of time. So with this method, which I recommend using in essentially every Keras training setup you're doing, whenever you're using transformers models and Hugging Face datasets, you just call this one method and you get a data set that's just ready to go straight in model.fit. And so you get clean results, top performance, and a minimal of wasted effort and boilerplate code. So that's the method I wanted to show you today, and I hope you find it useful. So thank you very much. Hey, everyone.
So thank you very much for that talk, Matt. That was super nice.
Yeah, that was very insightful. Thanks.
We also appreciate the little dig at PyTorch.
It's important to be clear where my loyalties lie.
Cool. So we have a couple of questions. So let's see. Here's a kind of great question, I think, about the way data collators work. So I'm just going to put it up on the screen. So the question is, does it make sense to sort the data by length so we get less padding per batch?
So that's a clever idea. That would actually work. You would then get these batches that would only be padded a small amount. The problem then is you're not sampling your data randomly. So all data would end up being batched together with the same other samples. So you would not get a random shuffle of your data set if you did that. And that would mean, especially if you're training for multiple epochs, your training would start to have very weird properties. Because of that lack of random sampling. So I don't think it would work in practice. You might get away with it with one epoch of training, maybe. But even then, I'm not sure I recommend it.
Great. So then we have another question, which is about zero-shot models. So if you have something like a zero-shot model, how does the TensorFlow auto model for sequence classification change? Okay,
that's a really good question. So in the example I used here, I started with Distilbert, and Distilbert is a language model, not a sequence classification model. And so when you put Distilbert in TF auto model for sequence classification, it basically sticks a classifier head on the like very last layer of Distilbert and just randomly initializes those weights. So that will not be capable of zero-shot classification. So if you want to do zero-shot classification, you need to start with a checkpoint that was trained on some sequence classification task in the past so that it will have the sequence classification head. And then you do zero-shot classification by just applying that model directly to your data without training. And the hope is that if it was trained on data in the past that is relatively similar to your data, then you will get zero-shot classification out of it. But that you will never get zero-shot classification from a base language model like Distilbert base. just because it has never done sequence classification before. So it always has to be trained with some label data.
Awesome. Yeah, I think what you can also do is use like natural language inference as the task, which is kind of like an elaborate classification task. If I remember correctly, that's actually how the zero-shot pipeline is based on. So you could do that in TensorFlow pretty easily.
Oh, yeah. If you can reframe the question as a natural language question, then get completion out of that, that would also work. Okay,
so we have another question, which is maybe coming also back from my talk. So imagine I have like an imbalanced data set. Do I need to worry about preserving the imbalance, like the class distribution per batch, or is this not a problem?
It's a good question. So I don't think it's necessary to perfectly balance per batch. Lewis, I don't like. Would you agree or disagree with that? I agree. I might oversample over the whole data set. I might oversample the rarer classes. I don't think I would care that much about balancing every single batch.
Exactly, and each batch is only maybe 16 to 30 examples on a single GPU, right? So I think this problem is going to kind of wash out in the average.
Remember that we trained plenty of classification model in ImageNet, which has like 1,000 labels, and its batch size is not 1,000. So
But it can be very helpful to oversample the rare classes. Even if you don't put them in every single batch, to still sample them more often than they would randomly appear. That is definitely a method people use, and that works well.
Cool, and maybe I can ask you a question. No, it's going to be fine. So I think one of the really exciting features in the TensorFlow API that you've been developing has been this kind of conversion of datasets into TensorFlow datasets. At least myself, this was always a pain point in like bridging the gap from, the Hugging Face ecosystem to the Keras one. And so I was just kind of curious, like what's on the, say, roadmap for TensorFlow in Transformers?
Oh God, there's a lot of things. There's a huge Notion document of things you want to add. Things that are big on the roadmap is we want to get a lot of vision transformers working well in TensorFlow. So we've added some recently, and we're planning to add several more. There's been some great contributions from people in the community. So transformers are not just natural language processing objects. That's kind of where they started and they see the most use. But they're getting extremely good results for vision tasks as well. And so we want to make a push because like a lot of vision people who are working in computer vision use TensorFlow and Keras. We want to like make the ecosystem kind of available for them as well. Other than that, there's a huge list of fixes, particularly involving like big performance boosts, for example, generating text with TensorFlow language models. We're going to make that a compilable TensorFlow function, which is going to give it a huge performance boost, and hopefully even beat PyTorch, which is kind of my secret internal goal whenever I start doing these things. I want that to end up faster, be like XLA compilable, and it's going to really upset everyone else at the company.
We have another question coming from the forum. I understand that padding enables patching data points together, but too many padding tokens makes the computation very slow. What is the attention mask for? I haven't fully understood the purpose of padding and attention masks and the impact on speed.
Okay, so that's a really good question. So the reason for padding is that if samples are different lengths, if you want to put them in an array, the array is going to be square or rectangular. Basically, it's going to expect that every sample is the same length. So when we pad, we basically put these null padding tokens onto the end of every sample. And those are just there to basically bring them up to the same length, but we don't really want them to affect the computation at all. And that's what the attention mask is for. So the attention mask is the attention mask is the same shape as the input array, and it contains ones for real tokens and zeros for padding tokens. And it basically tells the model to ignore all the tokens with a zero in the attention mask. So you can, like I said, pad the whole data set, but then you end up with your attention mask mostly being zeros and most of your samples just being padding tokens, stretching off into the distance. And that's just very slow and very inefficient because padding tokens do still waste a bit of memory and computation time, even though we try and get the model to ignore them. So it's ideal to use as few of them as possible, and that's what this method is all about.
Awesome. Do we have any more questions, Sylvain?
I think did we ask the one about the maximum length?
Yes.
I think, okay. So we have no more questions.
Great. So
Perfect.
thanks once again, Matt, and I'll hand over to
Thanks,
Sylvain to introduce the next speaker.